Me. Very good. Hello, everybody. Welcome to another afternoon of the Build Conference. I'm officially declaring as of now that that clock is 4 minutes fast, so I'm not late. Okay, so today we're going to talk about a little bit more about the game scenario and some of the technologies that we've thrown into Windows 8 under the new operating system paradigm that makes game development even easier and even more appropriate than it has been in the past. So let's get started. I want to cover a little bit of today about the Windows runtime. I think that's really just the fundamental foundation of everything that we're going to be talking about this week. I'm making some recommendations about what are the types of languages that work best with certain types of game genres. A little bit on how to tweak your graphics performance, and then a tiny bit on threading and multiprocessing. A couple hints on how to do persistent storage, which is a little bit different in the new environment than it was before. Networking is pretty similar. And then a fair amount on input controls and the different form factors that are out there, and how do I create the best experience on the broadest range of hardware. So first, I'm going to cover a little bit of background here. Why are we here today? Why would I ever want to make a game that's designed for Windows 8 in the App Store? The answer is the entire operating system has been built from the ground up to focus on this smoothness interactive experience, which is exactly the kind of experience that games also typically want to have. You don't play arcade games at 4 frames a second. So all the optimization that we've done in the new platform has been to focus the resources of the machine on the current app that's in the foreground, which is, again, exactly what you need to deliver the best experience in a rich game. The other model that we're conveying to users is that applications are always running. That's really nice because it means that if someone else wants to play to talk to you about a particular game, it looks like it's already there. You can just click on the live tile and it will look like it's already running. So the live tile gives you an opportunity to keep your app in the user's mind pretty much continuously. And then, of course, the work that we've done in the operating system to guarantee to reduce the number of situations when your application might experience a slowdown due to some other application running. Right? Like I said, we've focused the operating system on the current application. And then we've also enabled various mechanisms where their applications can collaborate with each other. So you can share a screenshot out to mail. You can share an invitation out to mail. You can even share a link to your app in the current store page, so that if another user, if you want to make your app go viral, you put a share link there, and then any user will be able to send a link to your game out to them pretty much instantly. And then the other advantage is that the new model runs on the ARM architecture, which is a whole new range of users and a whole new range of situations for the current users where they may not be playing games today. If they're sitting on their couch, they don't really necessarily have a tablet. Until now with Surface, they could have a tablet there, and there's a whole new set of eyeball minutes that people can play your games in that they didn't have access to before. And then, of course, to make that work well, if you want to have people be able to explore your game during the bus trip or the commute, or be able to have a device that they only need to plug in once a day, we need to focus on the advantages of the new platform that enable the lower power consumption. Another chunk of work that we've done has also been to streamline the development process, and we'll see some of the things that we've done in this talk. But really, it's about helping developers focus on the core set of APIs that are important for this platform, and not having to worry as much about all the other possible APIs that are not necessarily relevant to that platform. And then, of course, we've made sure that when we created the new platform, we added all the latest APIs for every type of feature, whether it's 3D graphics or joysticks or game audio. The latest API from across the company is integrated into the platform. And then, of course, the tools team has worked with us really closely to make the experience of developing the content using these new APIs and the documentation and IntelliSense all integrated together so that it's a really nice experience. That basically, what that means is it reduces your barrier to entry in terms of the cost of developing a title. And then, to top it all off, as we'll see in some other talks, we've built into the operating system the store concept, which is a very simple way to get your content distributed to all the potentially billions of PC users out there. So this is sort of an overview of the API architecture. Fundamentally, there is this low-level construct, the Windows kernel, that's been around for a long time. We've implemented this app model interface that basically defines what an application is as a sort of a specific entity in the operating system that can be easily managed and installed and uninstalled. And then on top of that, there are APIs that support a bunch of key functionality like communications and also media and graphics. And then on top of those, we provide language support bindings into those APIs from the Windows runtime through 3 different languages that you can then execute pretty much the same core OS functionality through. So that's one of the key points that I want to cover today is, what do you mean 3 different languages? Why would I need 3 different languages? And the answer is this, right? Fundamentally, we have these lower level layers. You have an option. The first option is to effectively target this which we call the Windows Web App Host, which is the core technology underneath the HTML and JavaScript engine. And that model basically means that you can take, if you have an existing asset base in terms of code or art or something, or even your website that's already out there in terms of web and HTML content. So you've written a web game or just you've got assets on your website. Those all become materials that you can incorporate into an application very easily because that application model supports basically the same engine that's inside IE. So it creates a very easy way to go from an existing set of assets in terms of JavaScript code and HTML code and turn that into an application and get all those advantages that I listed in that previous slide. Like, effectively what it means is that if you take your website or your web game and you turn it into an HTML game and put it in the App Store, then what happens is that application is now signed by Microsoft. It means that once it's installed, your user's never going to have to click OK to get some plugin or download the latest version of whatever other components you have in there, right? You can get access to the, plus, in addition to saving the user that issue, you also have the developer opportunity to access core functionality inside the operating system that no website could really be trusted with right now, right? So that's what the advantage is of transitioning your code from the web onto the app platform. Now, for developers who have assets in the form of C# and maybe XAML code, we've also got another app model that you can use to implement and target your application at the same core native runtime technology of Windows through the C# language. And actually, you can use a variant of C++ there as well and get things like managed capabilities, meaning garbage collection. Or if you're a person who's got a lot of experience or a lot of code bases already implemented in C++, you can build your application, again, targeting the same core technologies through an interface that's called Core Window that's designed to allow you to write your own sort of intermediate framework, which this is what a lot of the game samples in the SDK do right now, all the DirectX samples do. And then you write your application on top of that using C++. So the point I want to make here is that whatever type of code base you've already got is the best place to start in terms of deciding what language to use. Now, there's a little bit to be said that, so even if you've just got a web page, you can start moving on to the platform immediately. And then what we have is if you find that, say, you want to make your content run on a broader range of hardware, meaning some potentially very mobile, lightweight devices, you need to optimize performance. And so for that, what we would say is identify hotspots in your code. It's the standard performance optimization problem that everybody faces. Identify the hotspots in the code and look at re-implementing those. And in some cases, you may find that some core algorithm of your game, maybe it's the AI, is taking a lot of time or latency or lag. So you could take that and translate it into, say, C++, and then project that back up into your JavaScript app. And now you've got the simplicity of having UI designers that work in HTML, lay out your user interface and your menus and so on, but you've also got the opportunity to implement your core game logic and your high performance, AI and so on, physics calculations could all be done in C++. So what it basically means is that you have this option to move further and further to the right, and as you do, you pick up better performance, lower latency. There's increased effort on your part probably, but if you really want the best kind of fluid experience that games often like to have, then you've got that option. So, but there's already examples in the store of all of these three types of games already today. So on the JavaScript side, for example, this is really the appropriate platform for creating games like we're seeing Cut the Rope. You would think that's a very highly dynamic experience, but there is plenty of performance in the platform to implement that using JavaScript. And you can actually use that same API to access Xbox game controllers, full video and audio and networking APIs as well. So you can create multiplayer technology as well. So the ideal, the obvious types of content to create for this type of platform, if you're that type of developer, is the types of social games that we see today on the web, arcade games, if their graphics are comprehensible, and then sprite games, puzzle games, adventure games, card games. Those are all great ideas to use for a JavaScript programmer. And Cut the Rope shows that it can be a really good experience. On the C# side, we have that adds to the mix. You can now use the XAML UI toolkit. You can render potentially even high-performance 3D graphics in that environment as well. And then you can also drive your user interface XAML code either through C++ or C# code behind. So there's a bunch of flexibility that offers, and so that lets you really deliver go beyond that previous model to supporting things like first-person shooters or 3D games like RPGs. And then if you're a C++ person, this is the solution that really gives you the highest performance, which really what that translates into is it means that your content's going to run on the broadest range of machines, because it's tuning your performance is what enables the experience to be good on even very, very mobile, lightweight devices. And also it delivers the absolute best performance in terms of latency that you would need for like a Twitch game. Even some of these relatively simple games often have very timing dependent gameplay elements. And so tuning that particular piece of code by using C++ is a good way to optimize that. So action-based platformers where it's very timing dependent. And then, of course, another example is augmented reality games where you're using data from the camera to try to infer information. Those are games where the latency of the end-to-end capture between the camera and the display is really the critical thing that you're trying to optimize. And so by using C++, you're really getting rid of any intervening layers that would otherwise be necessary. Okay, now I wanted to put a little bit of clarification here on the Windows runtime because it's really the foundation, like I said, of all of these things in the new model. And I wanted to compare it a little bit with the .NET runtime. So these are not either ors, first of all. The .NET runtime is actually used by the new app model if you're using C# or any of the managed languages, basically the languages that rely on garbage collection. Basically, the Windows runtime is effectively a re-implementation to some extent of the .NET runtime with a focus on primarily native code in terms of the implementation, directly plumbing into the Win32 APIs, but also the memory management policy has been modified for the Windows runtime to be focused on reference counting, like COM supports, and less on, and it doesn't support effectively automatic garbage collection. So if you use C#, you'll get the garbage collection because you'll get the additional functionality of the .NET runtime layered on top of the Windows runtime. Both of these, like if you've got .NET code today, you're used to running XAML. There's also XAML in the .NET runtime. It's probably a little bit tweaked. Some of the names of some of the things have been changed, Some of the motivation for that has been that the Windows runtime has been designed to be projected into those 3 different languages, whereas the .NET runtime was really focused on the managed languages, C#, F#, VB, and so on. So that required a little bit of renaming of some of the function names, and of course the memory management behavior. So the issue here from the game developer side is that the Windows runtime is probably the ideal one to use for COM operations. Like, so if you're using Direct3D, that particular DirectX API at least, and some of the other DirectX APIs are expressed as a lot of COM objects. And so if you're sticking with that sort of model, then the Windows runtime is pretty interesting because we have the same syntax that can be used to manage these reference counted objects also be applied to the DirectX objects as well. Makes for a fairly consistent model, especially since that in the C++ language, the Windows runtime includes a set of specific compiler extensions made to Visual Studio called C++/CX for COM extensions, which simplify the syntax of dealing with reference counted objects to be just about as syntactically shorthanded as managing managed objects in C# or C++ CLI. Everybody knows what C++ CLI is? Okay, it's basically the C++ version of a managed language. Anyway. Okay, so now we're going to talk a little bit about graphics. The key thing about graphics is that we have a platform of a large amount of hardware, and the range of feature sets on that hardware is also large. So there are DX9 chips out there in terms of their D3D feature level capability. There are DX10, there are DX11 chips out there. And the way we handle this is we have a single API called DX11, which has effectively 3 different modes. It can run in 9 mode, 10 mode, or 11 mode. And at each of those modes, you get a different set of features corresponding to the hardware of that generation of silicon. And the way that the system is set up is that each level is a guaranteed superset of the preceding level, as in you don't get functionality on feature level 9 that has gone when you get to DX10, right? So it's always upward compatible. But really the key to optimizing for performance and therefore targeting the broadest range of devices and the broadest range of situations that your customers are in, the key to that is this optimizing your application for those specific hardware levels. Yeah. So the way this works is when you write your application, if you're in the C++ model for sure, and then potentially in some of the C# models, you get to actually specify at the time you create your interface to Direct3D the feature levels that you know your code supports. You tell us what your code supports, and then we come back and say, okay, given what's inside this machine, we'll come back and let you know which of the ones that you support you should use, because it's the first one that we find. Okay, in this case, the lowest level that we find, or it's the highest level that we find, so it's the first one we find that actually is one that you provided. So this developer has said, I can support anything. I can support 5 different feature levels, or 6, I guess. And so if he's running on a DX9 chip, a 9.3 chip, then this is going to be the one that he gets back. If he's running on a desktop, latest, graphics card that or an SLI rig, it's got a DX11 board in it, then he's going to get back that top one. And then based on the information that you get back, you can decide then which code path in your app you want to follow. So this is when you create the device, the interface to Direct3D, you specify that struct, which is the list of levels, and then you get back the actual feature level that the implementation recommends that you use among that list. Now, suppose you were trying to develop, you've got a developer machine that's maybe it's a DX11 machine because it's a big desktop PC, but you want to develop for something like Surface. You can go in and set a limit using a registry key that's defined by a control panel that we ship with the SDK. And that control panel says, okay, if I select that to be 9.1, then what will happen is the API will only return 9.1 as the maximum feature level for your API call, and that will guarantee that you're exercising your 9.1 code path. And so you'll be able to validate that your application still runs on a DX9 chip, even though you've got a DX11 chip in the machine. And so that's a really convenient way to get a good understanding of the experience here. So I just wanted to point out here, the low-level APIs that I'm talking about right now for this high-performance 3D graphics can be accessible either through C++ or through C#. For C# access, you want to use some kind of intermediate library, for example, that provides the bindings between C# and Direct3D. There's a couple libraries out there, one that Microsoft shipped, but another one that's really popular is called SharpDX, and that's actually used by some of the applications in the store already. Okay, this is another little tidbit I wanted to point out here at this point, which is we actually have a solution for shadow buffers that's available now in DirectX 9. We pulled the functionality back from DX10 onto DX9 as part of Windows 8. And so there's a full article on MSDN on how to support that. So we've written a couple apps that have some demos that show how to do nice shadows, even on something like a Surface, and or another very, very lightweight tablet or a phone. And the way that works is you go through the steps outlined on the web page. Fundamentally, you can effectively use the same code that you would use in a DX10 sample. It just works now on the DX9. Some of that works because we effectively use shader model 4 of our shading language, our 3D shading language, on the DX9 hardware. Okay, there's another tidbit I wanted to remind people about, which is while we work within the operating system to make sure that applications are given the primary access to the system resources when they're foreground, there's kind of an exception to that, which is if the user is playing your game and they switch out to the start menu because they want to just check a live tile or something, we don't necessarily currently throttle back your application. So what we'd like you to do is recognize, that's because we know that you're going to be coming right back. After they check that live tail, they're coming right back to your game. So what we'd recommend to people do is check for the onVisibly changed event, which is pretty common. Certainly it's something that all of our samples using Core Window implemented. And that way you can do things like throttle your frame rate back. It's pretty common today in games, even on the desktop now, for a well-written game to switch to a lower frame rate when it's lost focus. And that way your application could say run at 4 or 5 frames a second, and then what other application the user is switched focus to will have enough resources to run. So a typical example is you fire up an MMO and then you want to fire up a chat client like Skype to talk to your friends while you're playing. If the MMO doesn't let go of some of the resources, as in if it still runs as fast as it possibly can, then it's really, really hard to launch Skype. So that's kind of the same thing that we're talking about now, only in the Metro context. This should just be, it's a best practice. It's a being polite to the rest of the operating system scenario. Okay, multiprocessing. We actually have, there's a large number of reasons why you would want to use multiple threads and multiple processes. And we see developers using a bunch of different approaches to those. And so we've included in the new platform a couple different mechanisms, several different mechanisms to enable the scenarios that developers have been targeting with multiprocessing. The first one, this is not really necessarily anything to do with the fact that I've got multiple cores in the machine. It's just sort of a related model where it allows me to treat chunks of my code as independent and switch back and forth between those in the middle of an instruction, effectively, is what it amounts to from a programmer perspective. So that I can write effectively chunks of code that run what looks like in parallel as far as I'm concerned. And the real advantage to that is it lets me write code where I don't have to decide exactly what order these different things happen in. And the way this is implemented is using the PPL task library, which is integrated into the platform. You have to include those headers, but it's part of the platform. And so in this case, you can have a function and call it with a clause that says, okay, wait until something else happens before you actually do this. And so my main thread is going along, and it delegates some work to this other function, and then only when that situation becomes true does that actually get executed. And then when it's executed, then it returns and executes the next function, which is the bar function, for example. And then when that is done, then the BAS function gets executed. But the point is, your straight line code that you've been doing all of this along doesn't have to know when any of those things happen. So I can be doing things in there that are like, I'll submit a request to the file system, and I just keep running. And then I have an event that says, okay, is my file load complete? And I just check that every time through my game loop. Is my file load complete? And eventually it will be, because eventually the thread system will recognize that, okay, that command completed, and it will execute my completion function. And then in the completion function, I set the flag saying, hey, my assets are loaded, and now I can start displaying that content. So it's a similar situation occurs when I've got network input. If I'm waiting for something on the network, I can submit a task like one of these and have it be in charge of updating any information based on that network data, and then the rest of my application can just keep running. And the nice thing about this application just keeping running means that you never glitch. In a client scenario like a game on the local machine, everything has to run fast and fluid and smooth. And just because some thread somewhere decided to do some file I/O doesn't mean that your user should then be blocked, or that the user's animations on the screen should start stuttering. Right? And so this model is really what it takes to deliver the real-time behavior that you need in an interactive experience. Now, there's another use for multi-threading, which is people want to try to improve the performance of their application. And they say, hey, there's multiple cores on this machine. I've got a bunch of different threads here. It sure would be nice if I could get all of those cores doing something, because then I'll get done quicker, or my frame rate will go up. I'll be able to run a more rich experience, have better quality graphics on the same hardware. And so the API that we provide in the new platform for this is called the Thread Pool. And we shipped a version of this in Windows 7. I think it's pretty much identical to the one that shipped in Windows 7. There was an earlier version that shipped before that, but it's been tweaked a little bit since then. But fundamentally, you have this option to create threads using this service that manages threads for you. And the advantage of that is that creating and destroying threads is a little bit more complicated overhead than you really want to use in a lot of situations. So by having the operating system effectively hand you a list of pre-created threads, and then you just use them and then return them to the pool when you're done using them, it's a lighter weight operation. Now, the thing to remember, though, is that by default, the Thread Pool API doesn't give you quite as much explicit control over exactly which threads run on which cores as it used to using, say, the standard create thread model. But what we've learned is that a lot of times people who took advantage of that control didn't necessarily end up with a better, more robust or implementation that scaled particularly well. And so our experience has been, we have a fair number of intricate code bases inside Microsoft, and people have ported those code bases over to the Thread Pool and found that, yeah, they don't get quite the same, they get to within about 5% of the performance that they used to get. but their code is now easier to maintain. The overall responsiveness of the application in terms of other applications being able to get threads when they need them has improved. And yeah, they're slightly less efficient in terms of utilization, but there's one thing I want to point out here, which is kind of a novel concept to most programmers, and it's because of the way silicon is evolving. Fundamentally, we're entering an era where processor utilization isn't what it was cracked up to be. What happens in a lot of these chips is that when each of these chips and cores has its own, effectively a thermometer inside. And that thermometer is measuring the temperature of that core. And when you use that core a certain amount, you get above a certain utilization, it may get hotter, which causes that thermometer to register that heat and then tell the clock scheduler of that chip to reduce the clock speed of that core. So, so there are plenty of cases now where, and certainly over the next few years, we will see cases where letting your application not get that last 5% of utilization is probably okay, because it just means you're less likely to enter a state where I got that extra 5% of utilization and then it downclocked me by 5%. So that's kind of the point there. That being said, we offer some helper code on, the link is here, it's on the web, that provides a syntactic emulation of the traditional threading model on top of Threadpool. And again, it doesn't provide all the control that you used to get by having the native create thread APIs present, but it gets you a much easier process of porting, because the syntax that you're dealing with is much closer to what it would have been. And yeah, there's another big pile of links. I hope you guys can get these on your websites, on your machines. Okay, and now we're going to talk about the fun stuff, which is game input. This is something where really the user interface to the game is really a core part of the experience. And the situation that we're in right now is that users have, each of them, access to a variety of devices, especially now that we have with Windows 8 the ability to link all of these together with SkyDrive, so your documents are effectively hot synced across all these machines. When you have the ability to go into the store and buy an application once and have it be free on your all 5 of your machines, you just pay once and it automatically becomes available on all 5 of your machines. Effectively, you buy it on the first machine, it becomes free install on the next 4. What that means is that your application is going to be running potentially across all these different devices. And that's a good thing, because it means that your users can play your game no matter where they are, right? There's no reason to say, well, gee, I'm sitting at my desktop, I guess I can't play that game now. Or I'm on the bus, right? Because the point is, you've got a tablet, it can play the game. If you've got a desktop, it can play the game. So in that sense, from the API perspective, we have, you know, on other platforms, you'd have to write completely different code, completely different products for each of these different form factors. But with the new Windows 8 platform, we have consistency of APIs across all these. In fact, we have binary compatibility across all of these, and we have consistency of APIs coming with phone. So what that means is that you've now got the opportunity to take your content, which you write once, and have your user be exposed to it. Like maybe they're standing in line at the bank, they can use their phone, maybe they're on the bus with their tablet, maybe they're in the living room couch or coffee table with a tablet or a convertible, maybe they're on their desktop in the den, and, or you know, so there's the opportunity. Now, the question is, what do we need to do as developers to make sure that no matter where your user is when he decides to play your game, how can he get the best experience at that point? And so the graphics APIs, like I've talked about, there's DX9, DX10s, there's some variation there. We have a mechanism to handle that. The control schemes are really one of the things that actually requires a lot of focus. the fundamental issue is that we provide the APIs across all these different things, but you need to make sure that they've been polished or supported on the right device. And so some of these applications, like a first-person shooter, you're going to use mouse look on the desktop PC. You have mouse to aim your look direction. That's why it's called mouse look. And then you have your arrow keys or your WASD keys to move around. Very common. Half-Life, plenty of games do that model. We actually added support for this to the Metro platform, and it's integrated in part of the core window API setup. So and the nice thing about it is the way that it's done is if you implement it using that API set, you'll automatically get the same behavior on a tablet using touch, where the user's finger is now steering their look direction around the screen just the way the mouse used to aim the look direction around the screen. And then this is also something that's popularly used in 3D RPGs, first-person games there. In that case, usually the experience of going into this mouse look mode or touch look mode is triggered by a mouse button down, unlike, say, the first-person shooter where it just is turned on as soon as you start playing for you. And then another mechanism is this concept of just click to go somewhere. So like RPGs like Diablo or Torchlight, those are examples of games that you just click somewhere and the character goes there. So you can use tap or click, either one. So there's a bunch of work that's already been done to make these as aligned as possible, make it easy as possible for you to make your application run in all those different scenarios that your users might be in. One of the ways we do this is we have some games and samples out there already that do this. For example, Marble Maze and some of the other ones support all these different inputs simultaneously. If you've got a user who would rather use the accelerometer to steer their racing car instead of touch, well, you can just make all that work. And what we find is that if you just take all the inputs that you get from these devices, scale them by, you need to put a scale factor in here because you're going to have to tune the intensity or the sensitivity of that control. You need to be able to tune that sensitivity independent of the other controls that are available. And then you just feed that, we just add them all up and we send that to the game logic. And so at that point, the game logic doesn't care whether that steering input came from a mouse or a keyboard or a accelerometer. The logic is all running just fine. So that's what our samples do. So there's Marble Maze does this, simple 3D game or shooting game, I guess. And so let's take a look at a little bit more of the zoom in on the mouse look, because for the mouse case, we actually put in specific code to make that work. So you can do things like first-person shooters and first-person RPGs. The way it works is, in those types of scenarios, the mouse actually need to be turned into a relative device. So we have to enter what's called a relative, or we have to get back relative data from the mouse, not absolute mouse position. And because really when you're playing those types of games, what's happening is the user is now effectively using the mouse to steer the crosshair of the application. And the cursor is really that crosshair. So the real cursor moving around the screen is distracting and it kind of does the wrong thing. And what you really want to be able to do is get back just the incremental movement that mouse made during the last frame and then sum that into your look direction. So the way that works is we added a specific event called that you can actually register for that returns back relative mouse data. And these samples show how to do this. And the thing that happens is that, one of the things we did is when you're in this relative mode, since you really are steering the cursor around the screen, we actually, if you go in and hide the mouse cursor, which you really want to do, then we make sure that when you turn it back on again, it's the same place, it's kept at the same place where it was when you turned it off. So here's the relative mouse handler code. You declare the handler and bind it, you register it as a handler. It's a specific mouse-based handler. All the other input mechanisms in Core Window are just called pointer. And that way, those pointer APIs are agnostic to whether your pointer is a stylus or a mouse or a finger. It's all the same pointer. But this, because it's specific to the game scenario around first-person shooters, is a very mouse-specific game, a mouse-specific API. And so that's what we use in our samples and those ones I just mentioned, so that the experience now can be specifically tuned for both the mouse user who's playing a first-person shooter and then the touch person who's steering their look direction with their finger on a tablet or a phone. And these are the relative delta information that you're getting back in the handler. So now that was the sort of gameplay user interface experience, but there's another whole section of the game, which is the menus. And in general, it's good advice to not have too many menus in your game because they're kind of in the way between the user's experience. They get in the way before he can get into the real experience. But one of the things that makes that easier is if everybody's consistent on how we manage those menus within our games. And so we're not heavy-handed about this. We don't have hardcore certification requirements like, say, some of the platforms do. But in general, these are the kinds of models that we like to encourage, which is, on the keyboard and mouse side, be consistent with the way most keyboard and mouse games work, which is, use the escape key to get into your menu mode or get out of menu mode. And then when you're using the Windows Phone, they've got a specific hardware back button on the bottom of the phone that is effectively how you get back to your menu or get out of a menu. So these are all examples of how you implement these same scenarios using on different devices. So when you're starting to play your game, you're going to have some button called play the game, right? I'm done with my menus. There's going to be a play button that you put on your user interface, and the person taps on that or clicks on that, and you start playing. There'll be one of those even on a keyboard game. You're going to navigate using your keyboard or click on it with the mouse. And on a game controller, you're going to typically navigate there with the D-pad and then use the A button to fire that. Again, game controllers are fully supported as part of the new platform because we hooked up the X-Input API, which is the same API that's used right now on the Xbox. So all your Xbox controllers, you can plug them into your Surface on a USB port, play a game. You can set the tablet down on your coffee table with the kickstand and play a game using that controller. Marble Maze, all those things work today. And then, like I said, the toggle between menu and mode and not is pretty consistent between all these platforms. On the touch devices, we're recommending that people use the swipe in from the top or bottom. That's our standard mechanism to effectively sort of pause the game or go into a mode of the game. It's equivalent to using the escape key on a desktop today. On the game controllers, there are actually a physical pause button which you can actually press on the controller. And on the phone, like I say, there's this physical back arrow key. If we're just moving around in the menus, people are just going to tap or click or use the arrow keys or a D-pad if they've got one of those. And if you're trying to go back to the previous menu, most of these applications you're going to have to create your own back control. Like all the applications that you see in the Metro store today usually have a circle with an arrow in it in the upper left corner when you want to go back to the preceding thing, like the news apps or the web apps or the browser. And then, of course, if you've got a keyboard, make sure the backspace key does that too, and then fine. And so if you lay these things out in your application, you can actually implement all of these, and then your users are going to be able to run your application, navigate the menus using the paradigms that they expect for whatever platform they're on, and everything will be consistent. There's one more trick I want to talk about here, which is right now we use things like swap chain background panel to connect your, say, 3D graphics with your user interface. But another approach is to create two separate views within your application. This is not something that's widely known. And then have your user menus switch back and forth between those two views. And then one of you can be implemented purely in Direct3D, the other one can be implemented purely in XAML or C#, and that way you get the best of both worlds. You can have the full access to your user interface using the full menu capability and the high-performance 3D for your main gameplay screen. And this is something where we're basically telling people a lot of times you'll have a gameplay like an arcade machine. If somebody rotates the machine, you'll lose track of where you are because the game will try to restructure itself. So in some cases like that, it's probably better to explicitly either block rotation or at least, what meeting am I late for now? Anyway, explicitly block rotation so that the user is not disrupted and they don't lose a life or a ship or some other advantage while the operating system is rotating the display. And this is how you specify your rotation angle that you would like to keep. See, we just basically locked this application into landscape only. Okay, I don't think I'm going to talk about this. One of the things I did want to say, though, is that we do have a mechanism in the operating system today to enable developers to ship additional app content within their game that maybe didn't fit in the original package. And so you could have your game download, say, additional levels, additional content, and put it in basically what amounts to the saved game folder on the system, and therefore deliver an even richer experience than what was in the original package. And so this snippet of code here shows you how to do that. Anyway, so the conclusion I'm trying to draw here is that we've got all these different devices. We have the opportunity to create, with these APIs, content that spans all those different devices. But the biggest opportunity, the biggest place where there's less competition is in the tablet space right now. Basically, a tablet is its own unique thing. It's got some of the advantages of the PC in terms of the size of the display and the quality of the graphics that you can render, and then also primarily the duration of the session. People on a phone, they want to play for 3 to 5 minutes. On a tablet, they'll play for half an hour, because they're usually sitting down on a comfortable surface. So the thing that we're seeing is that nobody's really written the killer app yet for a tablet. No one's focusing on combining the best advantages of the PC with the mobility and the touch interfaces of the tablet. So that's where I'd say is the big opportunity for you guys. And these are our list of samples. So you're going to see this slide a few times. And that's pretty much it for my talk. So we're supposed to do QA. Surely there's something in the back of your mind you'd like to ask. Some point in the future, will this extend to Xbox as well? That's a really good question. And no, I can't answer it. Okay, here.
It's not really about games per se, but it helps to create a kiosk application. Is there a way to create a kiosk app using the WinRT runtime and APIs so that it can just stay in that one app?
Geez. So the question is whether you can create a kiosk app, meaning disable the app switching solutions.
And charms.
Yeah. And that's a really good question that I don't know the answer to either.
Is there another session that might be better for that?
Well, what we'll do is we'll ask around somebody. Somebody here should know that. Okay, over here.
This is the first winning talk that I've heard. Talking to DirectX through C#. Can you talk a little bit more about that option?
Yeah, talking to DirectX through C# is kind of tricky because it's, you can use things like pinvoke. We've got some actual wrapper code that Microsoft shipped was part of Windows 7 that helps with that. But the most popular solution out there is a technology called SharpDX, which is not from Microsoft. It's a third-party solution, and but it's very popular. It's I guess attempting to make that a really streamlined experience, and it seems to work really well. You should just look it up and try it out. Hey.
Such an HTML thing like up the road also works on Windows Phone
So we're working to align the API sets there between the phone and the PC. And so some of these APIs and languages are more consistently aligned than others. I think that the C++ model is very aligned. The C# model is also somewhat aligned, although their XAML code is a little bit more like Silverlight than ours is on the Windows side. On the JavaScript side, I don't think there's as much alignment as you could just say, okay, this will work, right? So I think on the JavaScript side on the phone, it's still, it's not present in Windows 8. Over here now.
Do you have any APIs for the avatars that were available in Game Studio or available in Windows 8?
The question is whether the avatars from Game Studio will be available on Windows 8. And the answer to that is I don't know. I think that is something that the Xbox guys are working on, but it's going to be a question of whether you're, what your relationship is with them, whether you'll get access to those APIs.
Does Windows 8 phones still support XNA?
Yes. The existing XNA model runs, you can write a Windows 7 app, Windows Phone 7 app today on XNA, it'll run on Windows Phone 8.
Did you write a new game in XNA on 8? Does it have to be the existing one?
You can write a new game on XNA and it'll run on whatever, on
What
both.
about RT?
No, the XNA doesn't run on Windows RT. It runs in Classic, not RT. But again, if you use SharpDX, okay, green shirt.
With SAML, we get a lot of feedback that the OS gives based on the swipe gestures and charm bar access. And I haven't been able to currently find any of that access at a core DirectX level using the core window. Is that something that will be coming out or is something that's missed?
So are you looking for the ability to have a nice library that implements those?
I'm looking to let the OS detect some of those system gestures like the charm bar, or more importantly, the app bar, instead of having to write my own with the OS.
Yeah, we have, there is a callback, for example, in Core Window that is called in your code that you can register for in Core Window that is the invocation of the app bar. And it is based on the same OS detection code that detects the movement that is used in XAML and in JavaScript code. I thought one of our samples on the Core Window samples actually did that.
I've seen some use the SAML to do it, but I haven't seen any just project.
Yeah, so what a lot of times people do is like if you've got a game like say Fruit Ninja and you're worried about people accidentally invoking that bar, they register the handler and just return null.
Yeah, we're actually trying to detect it.
And use it. Yep. Now, sure, that's in there. I swear at least one of our samples did that. The thing that it doesn't do is it doesn't render it, right? You've got to use your own D3E code to render that or DX code. Yeah. Yeah, I just can't remember which sample it was. Yeah. Okay. Is my time up on questions? Okay, back there.
Elaborate a little bit on where the balance of power voltage between if your app and operating system, your application is suspended. I heard another speaker say that you're notified so you can save state before your power is taken away. You mentioned that it's not necessarily problematic.
Okay, so there's a couple, the questions about how we do state management, process management. There's several good talks on this. I think our DDC talks and there's a developer conference from May that covers a lot of this. But fundamentally, there's two different ways to get occluded. One is if you get occluded by another app, and the other is if you get occluded just by the start menu, which is assumed to be just a transient thing. So we don't necessarily do anything to the foreground app if we just bring up the start menu because we assume it's going to be transient. But in the usual case, when I'm running some application, I switch to another application, it occludes the previous one, the OS detects that and says, okay, let's deprioritize the application that's occluded now because we know the user's not paying any attention to it. And so we do things like we don't give it as many thread cycles, right? It just doesn't get executed as often. But so what that, and then eventually we may just completely wipe it out of memory. So you do get a notification of that, but yes, it's only a few seconds of advance notice before we're going to do that. And the important point of that is that means that since you really don't know when the user is going to switch to another application and cover yours up, you really need to be making sure that you sort of journal or log the user's progress in your application pretty much continuously. Because that way, if you do actually get suspended and then flushed from memory, you can resume with the state that you had, and the user will not have lost any progress. Especially if it's something like a game, you don't want to say, okay, start over at the beginning of the level just because you swiped out to check Skype and came back, right? You want to be able to save your point even in the middle of a level, ideally, of your game, just continuously. And that way, when you get this notification that says, hey, you're about to be PLM'd, you can say, yep, that's great, because I'm already signed off. Maybe what you could do is you could use it to close some open file handles or something like that, but it's not really the point in time where you should be dumping out a 30 megabyte save file like desktop apps do today. Does that help? Okay, so the question is whether constantly saving a lot of state is going to be bad practice from, say, power management, power consumption perspective? Oh, okay, yeah, from roaming. Yeah, so first of all, you do want to be efficient with saving your state. If you're just saving like the player position in a game and maybe the current time or something, maybe some of the enemy positions, it's only a few bytes. But in general, no, we don't recommend that you save game information out to the roaming subfolder, right? There's this folder tree of your app local data where you can put things like save games, and then there's a roaming subfolder within that. The way we recommend that is that you put the save game either on that local machine, or encourage the user to put it on SkyDrive, or put it on your own server using Azure, and then just store a link to that in the roaming folder. Because that way, the amount of actual information that has to get replicated to every machine that user uses is just the link, not the 30 megabyte save game. Anybody else? Okay, here. I'm not sure what we announced on that, but yeah, there are a fairly large number of Windows Phone devices that use DX9. Well, again, everybody uses the DX11 API syntax, but some of these devices, like say Surface or the very, very lightweight tablets where they're focusing on power efficiency, run DX9. And so the phone is in that category too. In the future, who knows? I assume there are phone talks here, right, today? Yeah. Cool. Might have time for one more if my watch is still not wrong.
What's your favorite game?
I actually got into Mahjong there for a while, but actually things like Fruit Ninja and Rocket Riot are the cool things. I did want to mention something like Rocket Riot. What they do is a really good job of mapping to all the different control schemes. So when you're running on your phone or on a touch-based tablet, you don't have a keyboard or anything attached. They use the touch joystick, virtual joysticks to steer and shoot. Works really well. But if you're sitting on your desktop, you're using your mouse. They actually have a giant, targeting cursor that they use with the mouse, so you can bomb parts of the environment very explicitly with the mouse. And it's really taking advantage of the full spectrum of solutions that the platform offers to make sure that users get a great experience no matter what they're on. I was quite pleased with that one. Okay, well, thanks very much. And I'll be up here or at the networking session right after.